Good afternoon. Today I'd like to teach you a little bit more about current. If you remember from one of the earlier videos, we learned about current as being when charge moves from one location to another. Now specifically, current is defined as the amount of charge that moves past a certain spot per unit of time. As a formula, that is the amount of charge, delta Q, divided by the amount of time, delta T. And the symbol we typically use for current is the letter I, although I have seen in some books other letters, I think J. I'm going to specifically use I. The units for currents are amperes, I think. I'm probably slaughtering the pronunciation, but we never call them that anyways. We just call them amps. It's named after a person, Gustav Ampere. I'm not sure, but that's why we use a capital letter M. But amps is how it's abbreviated, and a nice equivalency to memorize is that 1 amp is equivalent to 1 coulomb per second. Now, an amp is a relatively large amount of current. A lot of the day-to-day small things that you work with, like calculators and phones and whatnot, they tend to operate more on the order of milliamps. So the little lowercase m stands for milli, and that means 1,000th of an amp. So typically, if we get a measurement in amps like 0.2 amps, if you move the decimal spot over 3 spots, that's 200 milliamps. And even a current of that much could be potentially dangerous. But current does have direction associated with it, and when we draw an arrow, for instance, representing current, that's the direction that positive charge would flow. It's kind of unfortunate that things are designated that way because positive charge, which would be protons are usually stuck inside of the nuclei, and they can't really get out or flow very often. Typically, in a circuit, what flows is actually the electrons. They're on the outside of the atom. They're free to move. And so usually when we talk about current and what direction it goes, in reality, the little tiny particles of electrons that move really go opposite the direction we discussed. But for all intents and purposes, it doesn't matter the direction so much as the magnitude, how much. So one important rule when we're talking about different circuits, and some circuits can be very simple and some can be quite complex, but an overarching rule about current is that the total amount of current that ever enters into an intersection has to add up to the total amount of current that ever leaves an intersection. So a couple of simple examples of that. Here at this intersection, I've got 2 sources of current coming in, 2 amps and 7 amps. And so the total coming in is 9 amps. That has to equal what's going out. And so this part that comes out must equal 9 amps. Here I've got 2 intersections. And so let's look at each one at a time. If we look at this first intersection, I've got 13 amps that are coming in, and 2 different currents leaving. I've got 4 currents leaving out along the edge here, and a total of 9 must be coming down. By the way, the answer is not always 9 amps. It's just a coincidence here. And so at this intersection, I've got 9 amps coming in, and 3 go to the right. That leaves 6 to go to the left. And so pretty simple. Sometimes it's useful to take a step back, and instead of focusing on these little intersections in the middle, if I were to draw maybe one giant intersection here, as a whole, there's 13 amps coming in, and then I've got 4 leaving here, 3 leaving here, so 7 so far are leaving. That means this has to be 6 amps as well, and that's what we calculated earlier. And so if a circuit's getting a little complex, perhaps draw a big intersection and see if that helps to analyze things with current. Here's an example of a relatively complex circuit. if I were to draw and kind of erase this complexity in the middle, I've got a total of 8 amps coming in. There must be a total of 8 amps going out. And so this bottom current we'll eventually find is equal to 8 amps. But let's take a look at each of the junctions in between. Here, this junction, we've got 8 coming in, 2 are going that way, and 6 then must be going this way. So if I look at maybe this intersection, I've got a total of 2 coming in. I've got 5 going out, so I must have another 3 that come in through this route. Let's see if that makes sense over here. 6 coming in, that means 3 could go that way, and that would leave room for 3 more to come out here. And so if 3 amps are coming in this leg and 5 amps on this side, it's a total of 8 coming in, and so 8 must be going out, which is just what we said it would be. So that's current. Now, there are lots of different examples of current that shows up in real life. As we watch some more videos and do some more assignments, you'll see some come up, but I wanted to just show you a couple. About 1 milliamp is typically about how much current it takes for you to kind of feel a little bit of a mild shock. And so if you increase that a little bit, about 5 milliamps can start to be kind of painful. About anywhere from 15 to 20 milliamps can be actually significantly painful and sometimes cause you to lose muscle control. That might mean you can't let go of a wire and it would just continue to run current through you. And potentially 100 milliamps might even be fatal. And so you want to be careful when working with current to make sure that you don't have a lot of it running through your body. Just a couple other examples of currents. I looked on the back of my monitor, and my monitor says that it runs off of 1.5 amps, so 1,500 milliamps. That could be quite dangerous if that went through my system. I think a dryer tends to be one of the most current-hungry devices you have in your home usually. 30 amps is a typical value for just a standard electric clothes dryer. So currents could run a whole range of different values, but there hopefully gives you a little bit of an idea of some so that you can understand it as we look at some more examples. Now, the next topic I'd like to talk about just the idea of resistance. So different materials resist current to different amounts, and that quantity of how much current or how easily current flows through something is called its resistance. So some objects are very good at resisting current, and we call them insulators. So plastics, air is a relatively decent insulator, and so forth. They are of what we call high resistance. And then others are very poor insulators. We call them conductors. So most of your metals are pretty good conductors, although some metals are very good conductors and some are only kind of good conductors, and so on. And you can put a number to that. The unit of that number is measured in ohms. The symbol here is the capital Greek letter omega, and so we just call them ohms. And another equivalency that you might want to memorize: 1 ohm is equivalent to requiring 1 volt to produce 1 amp's worth of current. So if you have, say, a 6-volt battery, then that could produce 6 amps. If the resistance is 1 ohm, so on. In general, the more resistance something has, the more voltage is required to produce a given amount of current. So that can be summarized in the equation. Potential, or voltage, is equivalent to current times resistance. And I find that this little, I call it the button, this little button is pretty useful for me to calculate different things, because there's times you need to find current, there's times when you need to find voltage, there's times when you need to find resistance. This button works if you're looking for current, then you would cover up current with your finger, and what's left is V over R. So if you're looking for current, take voltage and divide it by resistance. And if you're looking for voltage, then cover up voltage with your finger, and what's left is I times R. And if you're looking for resistance, which is probably the least likely, but if you're looking for resistance, you can cover up R, and that's just volts divided by current. Volts divided by amps. That's what an ohm is defined as. So here's a few examples. Suppose I want to push 3 amps through a 6 ohm and an 8 ohm resistor. How much potential would be required to make that happen? So the potential, or the voltage that I'm looking for, is found by taking V is equal to IR. So the current is I. The resistor, the first resistor here of 6 ohms requires 3 times 6, or 18 volts, to push that much current through here. Then I also need to push that current through here. It doesn't just stop here. Current has to keep going, and so 3 times 8 is 24 volts. And so as a whole, 18 plus 24, I would need 42 volts in order to push 3 amps through this pretty simple pathway. Down here are a couple other examples. I forgot to mention it earlier, by the way, this zigzagged shape. If you ever see that in a schematic or in a circuit, that is a key for resistance. So here's another resistor, here's another resistor, here's a couple more resistors. Here's another symbol. This symbol typically is a symbol that's used for some sort of a battery. And so I've got a battery that runs through a 30 ohm resistor and then back through again. So this circuit doesn't really serve a good purpose unless it's a heater. Suppose a toaster would have something like this on a much higher voltage. But anyway, what sort of current is running through this resistor and through the whole system? So if I've got 6 volts that run through this, then and I'm looking for current. Current is, if you cover up the I, you get V over R. And so that is 6 volts divided by 30 ohms, which works out to 0.2 amps. And so you might think, oh, that's kind of a baby current. But 0.2 amps is a lot of current. If you move that over 3 decimal spots, that's 200 milliamps. And well, even 100 can potentially be fatal in the wrong situation, so this would be kind of a dangerous one. Thankfully, your body has a much higher resistance than 30 ohms, and so 6 volts is not likely to produce that much current through you, but anyway, that's what it is, sorry. Here, I've got 2 batteries set up right on top of each other, and so if we call this maybe 0 volts, then in between here I'd be up to 8 volts, and up at the top I'm at 16 volts. And so those 16 volts are able to push current through the 500 ohm resistance. How much? Well, current is voltage, so 16 divided by 500, and that is 0.32. Let's check here. 16 over 500, so 0.032 or 32 milliamps. So this last example is a preview of some stuff we'll talk about in a few videos when we talk about more advanced circuits. In this first example here, I've got the two resistors kind of set up in a line. That's what's called in series. And down here, these two resistors are set up so that they're both attached to the same wire at the same voltage of 6 volts up here and 6 volts here, and leaves and has 0 volts down here. But these two resistors are parallel to each other, what we call in parallel. And we'll talk about the difference between setting up resistors in series or setting them up in parallel, and why you might want to do one versus the other in the future video. Suffice to now to say that everything on this top wire is at 6 volts, because that's at the top part of the battery, and anything along this bottom part is at 0 volts. And so there's actually two different paths that the current could take. The current that comes out of the battery could go down here, or it could go through this resistor. And in fact, there's 3 different values for current. There's current that goes through here. There's the current that goes through this part, through the battery. And then at this junction, this current splits into these two. And then at this junction, these two currents combine again to form this third. So now there's actually 3 different currents that we'll have to calculate here. Let me clean this up a little bit. We've got 6 volts, 6 volts, 6 volts, 0, 0. So through this first resistor, I've got 6 volts over 50 ohms, and so that works out to 6/50 is point. Oh man, I forgot already. 6 over 50, 0.12. So I'm going to say 120 milliamps runs through here. And then here, 6 over 100 is half of that, so 60 milliamps runs through here. And so if 120 comes down through here, and if 60 comes out and goes around through here, then 60 plus 120 means 180 must go through this circuit, or this part of the circuit. So there's a few examples of current and resistance.